We'll switch gears a little bit. We'll come back to microcontrollers and programming again, but I want to get started with, in a parallel thread, we want to start with the basic concepts behind sensing, right? And some of the formal details that we want to cover as a part of this course. So just to recap what we had done so far, as I promised, I'll go with both microcontrollers and some of the concepts in sensing side by side, so that I can also help you in understanding the sensing algorithms from an implementation perspective, right? So that's why I'm trying to cover both of them simultaneously. So far, as long as microcontrollers are concerned, right? So the things that were covered so far was some quick introduction, right, to the processing unit, and in particular concept of this instruction set, which is going to continue for quite some time as we try to delve more and more into different functionalities that are available in the microcontroller. Right? So we want to interact with the hardware. We need to know the set of instructions that are required to access them. So I gave some stress on these different kinds of instructions that we have, and some background about how an instruction is executed. And I also asked you to read the book, right? If you read several pages, right, in chapter 2 there is some, and in probably also in chapter 3, right, you'll have a very good idea about the basic thing, right? How the CPU operates and how instructions are executed. You are not expected to know much more than that, as long as basic programming of this IoT systems is concerned, right? If you want to do something much more advanced, you want to come up with a new kind of a architect, like new kind of a system that you want to design, right, from scratch. In those cases, you will need much in-depth idea about which instruction set architecture to choose, or somebody was asking questions about these things, right? What CPU to choose and so on, right? What are the power requirements in your system? So those things will be at a much more higher level, right? If you want to design the complete system starting from the hardware itself, right? So in this case, we are more concerned with using some off the shelf components. In this case, I'm teaching you using a 8-bit microcontroller. Try to perform some sensing operations, write some algorithms on top of that, and so on. And then we moved on to a very important part about the memory. So in the microcontroller, we had so many types of memories that we have already seen, and you have seen how powerful the registers are, particularly the input output registers in controlling the different peripherals and the ports. So by now, if you have followed the last class, you know what are these microcontroller ports, how are they used for digital input outputs, and so on, right? I have marked them in yellow because we will revisit them time and again, right? This will be the kind of bread and butter of uh, the microcontroller related concepts, right? Every device that we study or every peripheral that we study actually talks via these registers or the input output ports, right? So we have to visit them again and again. And as I told you, also I have given an example in the last class that you can program the microcontroller in form of a sketch, the way we were doing using the setup and loop. If you are using this Arduino IDE, you can also write a complete C code if you are using this Atmel Studio or any other IDE which is directly used to directly program the microcontroller. You can use pure C using the header files provided by the vendor. Let's say in this case it is AVR, so you have to use some AVR specific header files. Or at the same time, you can also use assembly level program, right? Even in the sketch, I showed you that how can you combine regular C statements with the assembly level program, and which is going to reduce your program memory size, or is going to make it more efficient in terms of execution speed and so on. Okay, and we have a lot of things to cover more in microcontrollers, particularly on the top. If you see the others that I mentioned, these are the miscellaneous things that we want to cover, and particularly from a sensing perspective, right? So that's why I wanted to go to sensing first before coming back again to these concepts. So one very important concept is, how do you interface, how does this microcontroller talk to analog devices, right? Where the data that you are receiving from the sensor is not in a digitized format, right? This is more the raw signal that we were getting from the infrared sensor, format, that instance, right? And that uses this analog to digital converters, and this takes a big portion in your microcontroller based sensing, right? How does this ADC work, and how do you interface the sensors to this ADC, and so on, right? At the same time, we'll have sensors that directly may send you digital data, and for interacting with those, they are basically they understand this digital data. It's not an analog device, and you have to come up with some protocols in order to talk in between the microcontroller and those systems, right? The sensors. So for that, we have these different types of protocols under this digital interfacing category: the serial interface, this asynchronous receive transmit, SPI, I2C, and so on. So we will go into details about their implementation and probably see a few examples how to interface sensors using those things, right? And we'll have some discussion on interrupts, but interrupts are going to come up every time, right? So any sort of interaction with the external world the microcontroller has is via these interrupts. And before coming to these things, I'll in a piecemeal way, right, I'll try to cover some of these things that I have mentioned, right, that is required for you to understand before delving into the details of specific case studies, right? So for example, we'll try to see how an event detection takes place in a sensing system, right? Because sensors are mostly one of the main functionalities of a sensor is to detect some event, right? That is at the minimum a sensor is supposed to do, right? If there is a fire, it is going to set up an alarm. It's something of that sort, right? And we'll talk a lot about quantization, which is basically converting all these analog signals into the digital form that could be consumed by a digital computer. And toward the end, we'll look at other frequency domain tools and so on. That will come up much later, right? And then after we have sufficient confidence with these things, right, we will move on to the case studies, right, which is also going to help you like decipher or like choose different topics for your projects, right? You can either do a project which is just purely based on a microcontroller based implementation if you want to actually do a hardware project, or we can discuss about other simulations and all, whatever you are comfortable with, right? Or you can even, like last year there were students who used smartphones, right? Whoever is proficient in Android, you can even do a lot of these projects using the smartphone, because you already have a bunch of sensors in them and that is already interfaced, right? So all you have to do is the bunch of APIs that Android provides, and you have to implement the algorithm there, right? So there is not much touching the hardware per se. So mostly it will be in software. But yeah, if you want to even learn a little bit on the embedded side, it's recommended that you work directly with the microcontrollers and the sensors, right? So that will give you a much more raw flavor of IoT systems. Okay, so I'll not proceed anymore here. So today we'll talk about I'll start with the sensing, and in particular we'll try to see event detection, right? So as you see, all of these things are doing some kind of a sensing, and based on that it's going to take an action, right? For example, if you see on the left hand side, a temperature could be set in the air conditioning machine, and it's going to continuously monitor the temperature, and based on a certain level that has been set, it is going to either turn off the air conditioning machine, or it's going to slow down the fan, and so on. Similarly, if you see in the bottom right, we are talking about this touch screen, right? So there is some sensing modality that is continuously detecting whether the screen has been touched, right? So that your screen lights up. That is one. And not only that, it's also trying to sense where the screen is touched, right? What are the coordinates in the screen where you have touched, right? So that is not only just an event detection, but there are some details that are associated with that event. In this example, the coordinates of your touch, right? Similarly, in your TV, you have this IR. So using the TV remote is going to turn on some infrared waves, right? And on the receiver side, you are sensing uh, that particular arrival of certain pattern of this IR, and based on that you will know what particular action was actually requested, right? And on the right hand side we have this kind of DIY devices, right, that you will see find a lot of in the college projects, where they build all these very simple functionalities, right, using very cheap sensors, right? In this case this is ultrasonic sensor, where it is going to detect the proximity of your hand, right? So this is a some this hand sanitizer, and if you want to bring your hand pretty close by, it is going to dispense some of this liquid. So all of them, right, if you see they are doing some kind of event detection. They're trying to sense the data or get hold of the data, and then based on the data it is trying to detect certain event, and it is pre-programmed for that, right? And we want to probably get into the roots of how that takes place, right? And what is the theory behind them? How do you make that event detection more accurate? How can you increase the confidence of that event detection, right? That is the topic of today's class. So sensors are everywhere, right? And imagine this kind of a plant, right, which we many of us could have taken these things as granted, but at every individual step there are so many sensors, some sensing their weight. The liquid is being filled to exactly the same level, right, with some degree of error in all of the bottles, right? And they have to be sealed. They have to put the stickers around them at the exact same location, and still maintain pretty decent throughput, right? The amount of the quantity that is coming out through the supply chain. So it's evident that we have to learn about different kinds of sensors, and they could be embedded in our bodies. They could be in our automobiles, planes, cellular telephones, radios, chemical plants, industrial plants, and countless other applications, right? And on the left hand side I have shown a few pictures of them, and it's better that you start getting acquainted with different kinds of sensor, both analog as well as digital. So some of them, the cheaper sensors, they don't have a digital interface, they'll just have an analog interface, and it's up to the host computer or the microcontroller to get hold of the data, digitize them, and so on. But it's kind of a good idea to know that what common sensors are available, right? And uh, have a mental sketch about what you can do with those sensors, right? So there is no exhaustive list that I can provide you, but you have to like look through different literature papers, and do some even Google search in order to understand the what kind of phenomenon could be actually sensed by using this kind of sensors. So what exactly is sensing? It is what we want to do on a very broad sense, right? We want to collect information about the physical world, right? So this physical world has a lot of things that we want to collect information on, lots of dynamics that we want to know about, and we want to somehow capture that information. And we want to do that using a sensor, which is an electrical, mechanical, chemical device that maps an environmental attribute to a quantitative measurement. So note, this thing is very important. So whatever you want to sense, right, you want to, at the end of the day, you have to convert that into some kind of an attribute that could be measured. It has to be a quantitative measurement, right? If we say that how hot a surface is, you have to have a quantitative measurement for that. Otherwise you cannot really do any uh, computation on top of that, right? You have to somehow characterize that with some numerical value. If I know this is 40 degrees centigrade or 80 degrees centigrade, or and so on, right? So the precision is a different question, at how much how precise your reading is, how much error, what is the accuracy of your measurement. That those are completely different things, right? But you have to start with a device that has the ability to do a quantitative measurement. And its sensor is based on a this transduction principle, which is converting one energy to the other, right? Somehow it is taking one form of energy, it could be heat energy, it could be mechanical energy, and then converting it into another form of energy, let's say electrical energy. So I do have a list. I collected some of this information, but there could be more, right? And each of these individual quantities, you might actually have a different kind of sensor which gives out this measurable quantity on the right hand side. So on the left hand side, there is a stimulus, right? It could be we are trying to do something with sound, right? Ultrasound or infrasonic or even human speech. There could be sensors which are built around acoustics, right? And what we want to measure is, let's say it's a waveform and we want to know what is the amplitude of that particular waveform. What is the phase of that particular waveform, right? How is what is the spectrum of that particular waveform, right? What are the frequencies they're operating in, right? So if you are dealing with human voice, right, it has a very specific frequency range. It cannot be very high or very little, something which is very well defined. Or we want to know the velocity of that wave, right? So there are different things that could be measured, and each one has a separate principle to do that, right? You will have a specific kind of a sensor or and on top of that maybe specific kind of an algorithm that is going to in combination going to find out or measure or estimate, I would use the word estimate for that quantity. Okay, and similarly for electrical stimulus, you might have charge. A capacitor is going to store charge, right? And you can have voltage. You can measure what is the voltage, right? If you recall, what we showed in the in the first class was this IR sensor where we were doing all this step counting, proximity detection, and so on. And as we saw, the closer we went, right, the intensity of the IR reflection increased in the photodiode, and based on that we had fluctuations in the voltage. So yeah, all this phenomenon, right, maps to some kind of a sensing application or some kind of a sensor, to be precise. Okay, and then other examples I have given, thermal, optical, magnetic, and so on, and there could be much more than that, whatever I have covered here. So these are some set of examples, and uh, your task would be to look at them very carefully and then try to see which of these physical quantities are measured by what kind of sensors. Kind of know some of the off-the-shelf sensors that are actually available for doing them, right? So you don't have to memorize anything. It is just for your own knowledge to get more idea about this kind of sensors. Okay, so this is the basic working principle, how a sensor works. Let's say you want to, this is a dummy example, you want to measure the velocity of this wind flow, right? On the left hand side, I have shown the wind is flowing and there is this device, right? It looks like a windmill, but yeah, it could be something that you have created. And the way this is rotating, right? How fast it is rotating or how slow it is rotating, based on that velocity or that angular velocity, it converts or it produces some kind of a voltage as an output. Okay, so this is the transduction thing that is going on from the wind energy. This is being converted to a voltage, and this is the variation of voltage with time on the right hand side. So the amplitude of the signal is a function of the wind speed, right? So now, but we have no idea how does this voltage relate to the wind flow. We know that there is this function present, right? The amplitude of the signal is dependent on the wind speed, but we don't know what that function is, right? Because there is no universal function that is going to give me that. It is also a function of your device or the sensor. So this is the characteristics of the sensor, right? How much of wind energy is converted to what kind of voltage amplitude, right? And for that we have to do something known as sensor calibration. So this mapping, right, so this is basically a mapping from the quantitative measurement that the sensor has done to the thing that we want to actually estimate, right? For example, here we want to estimate the wind speed. So the voltage value maps to some value here in the x-axis, voltage, and this some in the factory or like wherever you have created this device, right? You give them the calibration chart. So whenever the voltage is detected as this much, I from that mapping I know what was the wind speed, what is the expected wind speed, right? And this calibration can also have errors, right? It will always all the devices will be a little bit different, right? So all those things will always come into the play, but there is some approximate value, right, where it maps to. Okay. And you can also have recalibrate the system. So suppose the environment has completely changed, or the calibration that has been done earlier is no longer working for some reason, right? Maybe the wear and tear of the device, right? In those cases you have to again probably recalibrate the system. Okay, so this is one of the most important steps, right? Once you get the quantitative data that you want to measure, then comes the role of the sensor calibration, and from that you can extract the data that you are looking for. Okay, so this is the basic working principle. And this voltage values that we were measuring, right, normally once it is available from the sensor, this is continuous in time, right? However, if we have the inability, right, to continuously do the measurement, right, with time, we have to discretize the time. The time will no longer be, and we will cover all these things later, but I'm trying to give you a hint about why it might not be continuous, right? It's, although the actual time is continuous, the way we were sampling the voltage, right, we are trying to read the voltage out of that particular sensor. You have to stop, read that, and then again do the next reading, right? So that will take a finite amount of time in every reads, right? And that is the time you are spending for sampling the signal, and what you will get is a discrete version of signal which has been sampled at every time instant t. So let's say there is a time instant t, every time, every time delay t, or like delta t, you get one sample. So it inherently becomes a non-continuous or like a discrete signal, right? So we'll be mostly dealing with discrete signals because that's what you manage to get from a sensor, right? You are not going to read infinitesimally small values in time. You are not going to measure in that small periods of time, right? So just keep this in mind, and we are going to elaborate on that later. Okay. So there are two kinds of sensors. One is a set called active sensors, which is actively sending a signal into the environment and measure the interaction of the signal with the environment. So one example was the apart from this ultrasound sensor, which sends the ultrasound and then receives the reflection of that. Also the IR sensor that we discussed, right? It was sending an, it was emitting a IR infrared ray, and it was getting the reflection back. It is actively sending, putting something into the environment and trying to decipher or trying to understand the context of the physical environment by looking at how that actively sent signal is interacting with the environment. Okay, and the other example is the passive sensors, which just records signals that are already present in the environment, right? So like the temperature sensor, so it's already this heat is present, right? Whether it's in form of the infrared or any other form, right? It's going to already sense whatever is present in the ambient environment. Okay, so even let's say you want to detect the presence of whether a Wi-Fi signal is present or not, right? What you can do is that you can just go to the required frequency spectrum. 2.4 gigahertz is one example, and then you can basically look for whether in those particular frequencies you have enough energy, right? That can tell you that somebody is actually occupying that particular spectrum, right? There is some Wi-Fi. It's not, it might not be Wi-Fi, it could be something else which is operating in the same frequency, but at least you would be able to do that, right? You are not sending anything, you are just directly passively listening to that particular frequency for knowing whether somebody is transmitting in that frequency or not. Okay, so today we'll discuss a particular use case, right? I'll illustrate this with an example of automatically turning on lights when somebody enters the room, and we define that as an event. So when somebody is inside the room, or somebody is present in the room, we are supposed to turn on the light that is indicated on the left hand side of the figure. And now when somebody leaves, we have to detect that he has left, and we have to switch off the light, right? And we want to do it using some sensor, right? So this is the sensor, and this sensor is tasked with this particular problem. It has to detect the presence. Okay, so we can still use something like the photodiode that we have already discussed, because you have some idea about it, right? And this is on the top. We can put this thing on the ceiling in front of somebody crosses the door, enters inside, we can figure out that somebody is entering. So there will be a presence or absence thing, right? So somebody is entering the room, and this IR photodiode, we already saw that there is this samples that are being collected by the IR photodiode, and some processing will take place, which is going to give out this detection thing, right? So there will be an event detector. That event detector is going to process these raw samples that are available from the photodiode, and based on the result, it is going to tell whether a person is really present or absent, right? It is just the estimation. So this is the detected event or estimated event, whereas this is, let's say, the real thing where a person has really entered or not, right? And based on the detector decision, it is going to take an action, right? So this is the actuation part, where here he is going to, here the system is going to turn on the bulb or switch off the bulb in the room, right? And just to refresh your memory about this photodiode thing that we discussed in the first class, I have reused the same video. So if you remember, we were using this infrared sensor, the IR sensor, and when I was bringing my hand pretty close to the sensor, we were seeing a increase in the voltage value, and that's how we were detecting proximity. So in this case also, we are trying to detect proximity, because when the person moves through the door, walks into the room, he is in very close proximity to the sensor, so we should expect a sudden spike in that value, and we want to detect that, right? So this is just to recap. So on the left hand side, we are seeing these raw samples, and please note that whenever I am bringing my hand pretty close to the sensor, it actually changes the value, it goes high, and we want to leverage this information, right? We want to use this as a sensing modality now, right? So these raw samples, we have to write algorithms on these raw samples so that we can detect proximity. So hope this is clear. Okay, and just to give you a hint about the data collection procedure, so on the right hand side we have the figure of the hardware schematic. So this is the sensor. The sensor is giving you the raw signal values through this pin, which is being read. So this is, by the way, analog signal, and it has to go through an ADC. So we are using this analog read API. We can discuss all these things later when we talk about ADCs and so on. But analog read is just the way we were doing digital read or digital write from the digital input output pins. You can also do analog read using a certain set of pins in port C, right? So you can do this analog read A0 is just one pin number where your this pin is connected, right? This particular data there, or the signal coming out of this IR sensor, it is connected there, and we are getting a stream of these data values that we have shown here. So this is a raw sample. These are the data that we are getting. Okay, so I've just did a runtime plot of that, and then we will also discuss how to push this data out to a remote computer and so on. But for today, we'll not go into the details of the implementation. We'll come back to that later and try to show you how to actually have this kind of a system to collect data, right? But this is mostly some programming using serial ports. Okay, so here, just for your interest, I have mentioned this API called analog read. So that is in action. And what could be the simplest algorithm here? right? One simple algorithm could be, so at every instant of time we are detecting, or we are basically estimating a certain value, right? And that value, if it is greater than a threshold, we can report that the person is present. And if it is lesser than a threshold, the person, we can report that the person is absent, right? And the threshold is indicated by this red straight line on the right hand side, right? Because the straight line, the threshold could be variable. The threshold could be at this location, right? Or the threshold could be at this location, and so on. Okay, so our task is to figure out what is the right choice of the threshold. Okay, so many of you have done different, if you have done some project, right, you will see people will do some heat and trial based on some experimental runs and then come up with a threshold, right? And if they actually take this system to a different location, this threshold stops working, and then they will say, oh, I have to change the threshold. They will do some more hit and trial and then put another value of threshold, right? You keep on changing the threshold, right? But what we are trying to do is that how to take a scientific approach in designing this threshold, right? We cannot just depend on the hit and trial method to fix that value, right? That is a common practice that is done by many people, right? Even in the industry, there are like cases, right, where they will try to fine tune a threshold based on trial and error, right? Because sometimes they don't happen to have access to all the models or the data that I will talk about. So in some cases it is acceptable, but that is not a principled or scientific approach, right? So how to determine this threshold, right? So can somebody tell me what are the different artifacts, right? If we choose the threshold to be very high, or what happens if the threshold is set to be too low, what happens? Can somebody yeah, give some light on this thing?
Yeah, when we set it low, even for a small change, also we will get the presence equal to true. And when we set it very low, very high, then we may miss some cases where the detection will be present, but it is not reported.
Yes, so it's basically going to result in some kind of overestimation or underestimation, right?
Yeah, yes, sir.
So you might actually underestimate whether people are present or not. So what exactly should be a principled way to design this threshold? Let's look at like the principles behind it. uh, okay, so everything is clear till now,
Yeah, yes, sir.
right? If anybody has some questions or doubts, please feel free to ask, right? So I'm assuming you have understood how we are processing the data and what is the problem we want to solve here. Okay, so here as you see that this underestimation and overestimation can be termed in this very simple way. So this is the actual event on the top, that the person was absent or present, and this is the detected event, right? What is the detection that we are doing from the raw signal or the raw samples? We are based on the threshold, we are trying to determine whether the person was present or absent, right? So based on that, I have color coded this thing. So true negative is the person was not present, absent, so it is a negative example, and I have also detected it correctly. So I have truly detected that the person was not there. So I have truly detected the negative case, hence it is true negative. And just the opposite thing for true positive, right? So it was a positive case, the person was actually present and my sensor was truly able to detect that. So it is a true positive case. So these are the places where the sensor has not malfunctioned, right? Whatever be the value of threshold, it has actually detected it correctly. If it was absent, I have reported it to be absent. If it was present, I have reported it to be present. Okay, and the other two things are kind of interesting. One could be that if it was really present, the person was really present, but I have told, so in this thing the person was really present, and my sensor thought he is absent, right? So it has falsely told it is negative. So it is a false negative. It's actually positive because the person was present, but it has falsely told that the person is absent. So this is false negative, and the other thing is false positive. I have falsely told that the person is present, where originally the person was absent, right? So many of you are introduced to this concept through many courses, right? But yeah, so it is just to rehash your memory, and sometimes these concepts become very confusing. So make sure that this is the basis of event detection, right? Once we try to characterize the performance of the sensor while we try to detect events, these are the things that you will need for sure, right? And this threshold is so important, right? In many of this hardware, right, in commercially available this IR photodiodes and IR emitter sets, right? These are they already come with a threshold adjust button, right? And this red LED that you see is for an obstacle detection thing, right? If an obstacle is detected in front of the robot or wherever you install this sensor, it is supposed to go on, right? The red light will be on, and otherwise it will be off, right? For just for doing that, depending on your scenario, this is the threshold adjust button, right? You can this is a potentiometer where you can rotate this thing, and this will adjust the value of threshold, whether you want to be too restrictive or you want to be too relaxed, right? In the sense, how far is your obstacle from the device, right? If you don't want to take any chances, right, even if you are like one foot away from the wall, you might say there is an obstacle and you want to stop, right? You don't want to take any more risk. Whereas if you are operating in a very small area, maybe you can tolerate up to a few centimeters, right? Maybe 5 centimeters. Within 5 centimeters, you want to report that, yeah, there is an obstacle, I need to stop. So this varied degree of requirements that you might require as a functionality in the sensor, that is why some of them come up with this hardware button where you can adjust the threshold. There is no software thing here because this is directly controlling the LED, right? But if you are reading this data out and doing something in the compute part, you can come up with some other way to detect that threshold, or you want, or like come up or estimate the threshold, right? It could be adaptive, or it could be learned from data, and so on. Okay, so based on these four metrics, right, the true negatives, or true positive, and the false negative and false positive, these are the very common metrics that we kind of associate this performance of the sensor with. Particularly, this is the precision and recall. So read very carefully. This is the definition of precision. Given the number of times the human presence was detected, right? Note that given the number of times the human presence was detected. So detected by whom? The detected by the sensor. How many times was the person actually present? Okay, so you could always tell that you could always tell for every sample you can report that the human was present, right? Probably your threshold was very low, so any value you get, you say yes, the person is present. So in that case, what will happen, you will still have some precision, because out of suppose 100 times you have reported that you detect the human presence, out of them maybe 30 or 40 times the human was actually present. So you basically, you don't need even any data to tell all those things, right? Every time there is a probe that please tell me whether the person is present or absent, you can tell yes, the person is present, right? So but that is going to hurt on a different domain, right? In a different kind of a metric it is going to be captured, where is that given the number of times the human was actually present, right? Uh, how many times was the detector able to identify it correctly, right? So just note the difference in the denominator. In the numerator, we are always trying to look at true positives. In both the cases we are looking at true positives, but in the denominator it is slightly different. In the first time, in the first case, in case of precision, we are trying to look at the detection, the positive detection by the sensor, whereas in case of a recall we are trying to look at the actual positive cases. Okay, so actual positive case is true positive. Of course, true positive will be there, and false negative. You have falsely told those are negative examples, but they were actually positive. Okay, and in this case, it is easy. True positive plus false positive because the sensor thinks those are positive. So both of them will come into play, right? So these two are very very important metrics when you try to characterize the performance of event detection, right? Let's say you want to build some sensing system where you are trying to detect even this event, right? How do you statistically measure the performance, right? So precision and recall will be your friends for most of these things, right? And accuracy is the overall correctly identified presence or absence cases, right? But this precision and recall are kind of really important to understand what kind of errors are more, right? Whether you have more false negative errors or you have more false positive errors. So there could be cases where false positive errors could be more expensive, whereas false negative errors could be less harmful. Let's say, right? Say, let's say the person entered the room, right? But you did not turn on the light, right? So it was actually positive. The person entered the room, but you have falsely said it is negative, right? So falsely you have said it's a negative, false negative thing. So you did not turn on the light. So this is fine. Maybe the person will turn on the light manually, right? But let's say the person has left the room and you have not switched off the light. In that case, it is going to just add to your electricity bill, right? You probably want to avoid that more compared to the other case, right? So there is a fine balance in between them depending on your application, and you have to decide based on your intentions, right? Your application's demand, that whether you want to have a higher recall or a better precision, and how do you want to adjust the threshold and so on. Okay, so now let's go towards a actual model, right? How do you have a little bit more formal way towards designing this threshold, right? Let's try to understand the background. So here in the plot we are seeing two histograms, right? So the first histogram is the red one. The left hand side one was the data that was collected without having the human near the sensor. So I put the sensor in front of the door, and if somebody was present, right, I was standing in front of the sensor. No, sorry, somebody was absent. That is the voltage readings that distribution of the voltage readings that it produced, right? That is the pink or the red one. Whereas if I was standing in front of the sensor, then I have collected a different distribution of this data, right? As marked using the green histogram. So the human present was standing near the sensor within a distance of 2 meters, right? And about 5-6 feet from the sensor, and then we collected this information and put them in form of a histogram. So these are the two different histograms that has been collected, and this is historical data. In that sensor, putting the sensor in that location, we have collected this data. Okay, and we can always try to fit a model to this, because this is historic data that has been collected, and we want to reduce this data to some kind of a parametric model. And let's say these are the, we have a Gaussian distribution that we want to fit here, and we basically from the data fitted these distributions. So how to do that? Anybody has a background on how can somebody care to explain how to do this, right? We have this data from these histograms and we want to fit a Gaussian distribution to that. How to do that? Yeah, I mean, if somebody is like sending a ping, it's kind of difficult, distracting for me to go back. So if somebody has an answer, you can just speak out. So this is a normal distribution, right? And what are the parameters of a normal distribution? This has nothing to do with
Mean and deviation.
sorry.
Mean and deviation.
Yeah, so the mean and the deviation, right? And then how do you have an estimate of the mean and deviation from the data?
I mean, mean would be the average of the whole thing, and deviation would be the distance, the sum of the average square distance from the mean to each of the points
I mean,
taken
yeah,
in
that is
the.
the definition of deviation. But what exactly you want to use as the deviation and the mean of the normal distribution is from the data, right? So yeah, as you said, probably from the data itself, we want to find out the mean of the distribution. That is what you are going to use as parameters. So these are the parameters uh, of our normal distribution. It need not be normal. I just took an example. This is a pretty common practice that is done in such data. You could have an exponential distribution or some other kind of a distribution, right? But in this case, let's say we go with a Gaussian or a normal distribution, take the mean of the data, and that becomes the distribution's mean. Take the standard deviation of the data, that becomes the standard deviation or the deviation for the normal distribution also, right? And then we have it for these two cases, normal 1 and normal 2. So these are the two different distributions, and they might have two different parameters, mu 0 and sigma 0, and this one might have mu 1 and sigma 1, right? And yeah, if you want to go into a little bit more on the statistical side, there is something known as unbiased estimator. So the estimation that you are doing for the mean has to be unbiased. So if you want to look up more about it or know more about it, you can. It's not that much of a thing. You can look at unbiased estimators. Okay, so yeah, it's nothing. It's completely orthogonal to our course of study here. But yeah, in case you want to know about it, so you can look it up. Okay, and so after we get the parametric model, right, we are representing the entire data using these two parameters, mu and sigma. We can get rid of the data. So the data is no longer necessary for us. Right? So we have these two distributions now, 0 and 1, and represented by these two normal distributions, n0 and n1. And these are basically serving as two models. One is the distribution of the voltage in absence of a person, and another one is the distribution of the voltage in presence of a person. Okay, is this clear? Are there any questions? Okay. Okay, so now we will have these new names called hypothesis. So it's still two distributions. One is absence, the other one is presence. We are calling this as two hypotheses. One is hypothesis 0 or a null hypothesis, where I say a person is not present. I have again marked them as absence in the plot. So, and the other one is presence. So this is a hypothesis H1, and these are the two probability density functions over the photodiode voltage reading as the random variable. So on the x-axis, the random variable that is being used is the photodiode's voltage, right? And all we have done, like earlier, we are using this the discrete data points, and we had the probability. We are plotting them in terms of a normalized histogram. Now we have the density functions, right, which are estimated using the data itself, right? So these are the two PDFs, I would say, right? And we are solely interested in the detection of H1. So the other one could be just delegated as a noise, right? You don't want to detect H0 per se, but we want to know when H0 is not happening. So we want to reject the null hypothesis. So H0 is known as, here we can have many different names. We are calling it the null hypothesis, or this is basically representing the situation when the person is absent, and using the data we want to reject the null hypothesis and see whether the person is actually present. If we are not able to do that, we are not able to do that, but we are trying to see that whether it is actually H1 that is materializing. Okay, so this is the abstract definition of the same problem, right? The way we were using this threshold and all, we are trying to solve this problem only, right? We were trying to tease, right? Like you can like slice and dice these two, tease apart these two distributions, whether it is H0, whether it is H1. Okay, so now the next thing we can do is basically, since we have these two PDFs, we can choose, right, for a given value of X, right? Suppose X is the raw sample that we have collected from the microcontroller, right? After the digitization of the raw signal has taken place, I get a value X, and what I can simply do is plug in the value of X in these two distributions, right? I have a distribution n1 or n0 for h0 and n1 for h1, and I can simply plug in these two values and see which one is bigger, right? So this is typically, you have already if you have taken a very basic course on statistics, you know these are the two likelihood values, right? Given the value of X, I can know in which one you are more likely to go, right? So an obvious approach for decide, so wherever we stopped was basically trying to uh, trying to identify which distribution to work with, right? And one of the obvious approach that I was talking about is to find out the value of the likelihood, whether plugging in the value of X, whether it is going to be P0X and P1X, and based on their values we can choose that particular distribution. Okay, and now if P1X is greater than equal to P0X, we can choose H1, whereas if P1X is less than P0X, we can choose H0. This is one straightforward way to approach this particular problem. And the other way, there is something known as the likelihood ratio test, where what we do is we take the ratio of these two, and P1X and P0X, and if it is greater than a particular threshold gamma, which is known as the likelihood ratio, then we sort of do the same thing. If P1X is greater than equal to gamma into P0X, then we choose H1, otherwise we choose H0. So we, instead of using gamma is equal to 1 that we have done in the last case, there is a, we we put a certain weight in this ratio. Instead of using it as a 1, we use some other value gamma, and this test is known as the likelihood ratio test. And we basically are marching towards a little bit more formal way to approach this problem or solve this problem. Okay, so any questions with the likelihood ratio test?
Sir, how to choose gamma?
We are coming to that, right? We are just setting up the scene, right? We are just setting up the context, right? So we need this tool called, or the weight called gamma. We have not yet decided how to choose the optimal value of gamma. Okay, now, so the performance of the likelihood ratio test inherently depends on the choice of the threshold gamma, right? So if you choose some arbitrary gamma, again it is going, we are going back to the same old problem, right? You are going to have lots of false positives or false negatives, and that also translates to a particular threshold value for the voltage, say theta, right? So depending on the value of gamma you choose, it is going to translate to, if you expand and solve this equation, it will, you will basically get that some theta is there, based if more than that theta you choose H1 or you choose H0, right? You can cross calculate, back calculate. So the approach that we want to take is that is a classical way of solving this problem, is called the Neyman-Pearson theorem. So this is your take home point to understand how this Neyman-Pearson theorem works, and this is a standard way to approach this particular problem and solve it in an optimal manner, right? We will see what optimal means in this case. Okay, so first of all, let's again come back to these two distributions. We have chosen a threshold theta, and we already know our algorithm works like this, right? If the value is greater than theta, we choose hypothesis H1, else we choose hypothesis H0. That is a simple code that we have written, right? And the red area, what is this? We call this is the probability of false alarm. So what is false alarm? False alarm is H0 is true, right? H0 is what? H0 is our null hypothesis, or the case where the person is absent and we have thought that the person is present. So we are falsely putting on an alarm that the person is present. The person is not present, we are falsely putting on an alarm, right? So that probability will be this much, the area under the curve on the right hand side of the dotted line. So it is still belongs to the distribution H0 because that is what that has materialized. The person is not there, but since we have chosen this kind of a threshold, there is always a chance that we are going to raise a false alarm. So I hope this is clear. Please confirm.
Sir, can you please explain once more this false alarm?
Okay. So okay, so the false alarm is I am falsely raising the alarm. I'm falsely reporting that the person is present because if the value of the variable is greater than the threshold, we are saying that the person is present, right? That is our algorithm. However, in this case, because the distribution look of H0 looks like this, on the right hand side of the threshold also you have some area under the curve, right? So this area that I have marked with now with these black lines. So this much probability mass is already there in H0, right? Which is going to be a few cases where you are going to have this false alarm, right? So you are going to choose H1 although H0 is true. So although the human is absent, you are going to detect that the human is present and turn on the lights. So this is the case of false alarm. And on the left hand side is what? On the left hand side is called misdetection. So let's say the value of the voltage will be in this domain, in this the shaded green portion, right? In a few cases of H1. So the person is present and the voltage that you are going to see while the person is present is not always greater than threshold, right? Then you will have a 100% detection rate, right? But you will miss some of the detections because the values will be on the left hand side of the threshold, but you are going to conclude that the person is absent because these values are lesser than the threshold. This is not on this side, right? And how frequently this will happen? If you look at this model, this percentage of times, right? Whatever we call the area under the curve in the misdetection, this much times this will happen where H1 is true, but you will choose H0 because your value is less than threshold. What can you do? The threshold is already chosen. So the human will be present. This will be H1, but you will detect it as H0. You will fail to reject the null. You will think the null hypothesis is true, right? So you will keep the lights off. Okay, so this is clear also. So these
Yes.
are like, okay, okay. And then we will have, so we don't normally work with probability of misdetection. What we work with is known as probability of detection. So this is just the other thing. So the probability of detection is the other part of the curve, right? So this was the probability of missed detection, right? How many times you miss it, right? So 1 minus p of pm is pd. So how many times you detect it? So this is pretty important for us. Probability of detection. So probability of detection and the probability of the false alarm, these are the two pillars of your detection system, event detection system, right? How much time, you, of course, you want 0% false alarm and 100% probability of detection, but as you are seeing, it is not possible because this H0 and H1 will always be overlapping, right? If you have these two distributions that are kilometers apart, I don't have a problem, but that is not the case. They are not kilometers apart and they will have some kind of overlapping, which makes the detection problem harder. Okay, so your event detection probability, PD, you want to maximize this, right? I don't want to have a lower value. I want to maximize this, right? And at the same time, I also want to minimize this. I don't want to have minimize, right? I don't want to have a very high value of false alarm. I don't want the system to set a false alarm every now and then, right? So what is the good way to do it? So if we simply change the value of threshold, here you can see I have put an animation. So we begin with PD is equal to 1, probability of detection is equal to 1, but probability of false alarm is also 1, right? Your threshold is very, very low on the left hand side, right? And as we change the threshold, you will see I will plot these two things. I will plot in the figure, I will show the probability of false alarm, the area under the curve, and probability of misdetection. So instead of PD, I'm just showing PM, and PD is equal to 1 minus PM, the other half, right? Let me show you this thing, right? And I can pause and show you in certain cases. So see, as I change the threshold, the value of the green portion, right, the value of misdetection, it starts increasing slowly. And on the right hand side, the red part, the false alarm is also decreasing, right? And the value of probability of detection, PD, is this big thing that is on the right hand side of the threshold bar in the green curve, right? I have not shaded that one, I have just shaded the probability of misdetection. So your PD is now 0.97, and 97% is your PD, whereas your probability of false alarm is about 30%, right? And now it is decreasing. So your false alarm has become much lesser now, right? But your PD has also gone down. Now suppose you just want only 2% PFA, probability of false alarm 2% is, let's say, acceptable. Now you want to maximize the value of PD, but you can't do it more than 80.81 is like 81%, right? Suppose you wanted a system that has a 90% PD, then of course you have to do a trade-off with respect to your probability of false alarm, because that will also go up. You can't help, right, depending on the choice of threshold. So now I have already reached a very low value of PFA. Okay. So its PFA is almost 0, and then there is no point increasing the threshold anymore, and both of them goes to 0. Okay. So what we try to do, we try to maximize the value of probability of detection subject to the maximum allowed PFA. If you tell me that I am happy with a 5% false alarm rate, I want to make this as much as possible. I want to maximize the value of PD, and for that I want to choose the certain threshold. That is how I want to find out the value of gamma, or the threshold that we were talking about for so long. Okay, so this is the way to do it. Okay, so how to do it? So let's say this is one instance of the threshold. So this is one instance of the chosen threshold, theta, right? And I want to find out that value, right? What to do? So for a fixed value of PFA, read this very carefully. For the fixed value of PFA, this is given to you that your event detection system should not have a false positive rate more than 5%. Right? So this is given to you. So the likelihood ratio test maximizes the value of PD with the following decision rule. So the decision rule was already known, that Lx is the likelihood ratio test that we are doing on the value of x, and then we want to have this value greater than gamma, where this threshold gamma is determined by in this way. So how it is determined? We are basically seeing that for which value of x, right? Let's say this is, or let me use the term x instead of theta. So for which value of x, this is the area under the curve from x onwards to infinity, probability of x under this hypothesis of H0, which means I am working with the red curve, right? This is the H0 curve, the red one, right? Is PFA. So this is the area under the curve. PFA is the area under the curve, which is marked as red, right? I am marking them in the figure. So the definite integral, I am basically trying to find out where it should start from, what is the starting point x, such that Px given the hypothesis H0 dx is equal to PFA. And given that the solution to this problem, right, this is PFA is provided, this is provided, this is 2% or 5% or whatever area that you want from the system, this is provided by the model, because you already have an idea about the null hypothesis, how you have already fitted the model, so you know, right, be it Gaussian, be it any other PDF function, right, that is a given model, right? And all you want to do is basically try to solve for x, right? From where should you start the integration from, such that the value is PFA, right? So this will give you the maximum value of PD. So this part is PD, as you know. The remaining part of the green graph on the right hand side of the threshold is this part, this area is known as PD, which is 1 minus PM. So this is probability of misdetection, PM, and on the right hand side it is PD. So you have to think about it a little bit more carefully later. So now I'm teaching it, but once it is done, you want to revise it on your own, you have to think about it very carefully. Okay, so this x is going to give you the optimal value for maximizing the PD. So any confusion or any clarification that is needed?
Sir, now if PFA is given and I know the probability distribution for H0, then I can straight away find X without any thing to know about gamma. I mean, I don't even need to involve gamma or the LX. I can just find X
No,
directly, right?
the way it is given is the likelihood ratio test. If you want to report the value of gamma of the likelihood ratio test, then only you need that, right? So just the comparison of these two probability distribution functions. Yeah, you don't need any what is it called H1 here, right? But you have to please note this thing, right? That Lx has to be greater than this gamma, and that is what you are calculating this X for.
So is there any other significance to gamma? I mean, in this plot, to find the threshold, I don't need gamma. But why do we need
No,
gamma
no, no.
otherwise?
Just to put it in the model of this likelihood ratio test, the way it is formalized, right?
Okay.
It uses this term called the likelihood ratio called gamma. Right? This is, of course, as I told you earlier, right? If you see this thing here, right? This basically maps to a particular voltage value, say theta. So this is the terminology that is used for the likelihood ratio test gamma, which theta is nothing but x here, right? So this maps to a certain value of x. Of course, you can go the other way around. So it is
Yes,
just
sir, got
trying
it.
to put these two things in perspective, right? I'm starting with this likelihood ratio test and then putting the same framework and introducing this Neyman Pearson lemma. That's all.
Yes, sir, got it.
Okay. But yeah, anything else? But yeah, as you said, like as you have already seen that, yeah, it depends on historical data, right? So this kind of although this gives you a formal framework to perform this operation for maximizing PD with a fixed PFA, but you are working with data that has been seen earlier, and you have already formed a model. So if your model is not correct or you have insufficient amount of data for this model, this is of course not going to work the way it is expected. Okay, so I'll take a few more minutes. I just lost power. Maybe I'll try to wrap up within 4 or 5 minutes. So just one more concept that is remaining here is called, it's very important to summarize everything in form of a plot known as receiver operating characteristics, or ROC, as it is commonly called. So all this these are plot versus probability of false alarm and probability of false detection, probability of detection, right? As you saw in the video, right, what we were showing is that as I change the threshold, right, I had infinitely many values of threshold, right? The straight blue line is moving on the right hand side, and you are continuously having different values of PD comma PFA, right? So all I have done is basically try to do kind of a scatter plot, right? For every value of threshold, I am getting this tuple PD comma PFA comma PD and then plotting them in this plot, right? And I can have a very small value of gamma or the threshold, whatever you choose, or a large value or a small value, and depending on that, I am going to have different values of PD and PFA, and the spectrum of these values. Note that the spectrum of all possible values for different possible values of the threshold or gamma is going to give you this ROC curve, right? So this is a curve that is chosen to characterize the sensor's performance. Okay, so an usual way of illustrating the detector performance is the ROC curve. This describes the relationship between PFA and PD for all possible values of the threshold gamma. The higher the ROC curve, the better is the performance. So if you have an ROC curve which looks like this, right, you won't be happy, right? So you are not getting very high values of PD for a lower value of PFA, right? I want to minimize the value of PFA. I don't want a very high PFA, right? At the same time, I want to maximize the value of PD, right? So this is a poorer curve, right? This is even more poor. It's kind of a random guess, right? Whereas the more picked the curve is, right? So something which is almost like this and like something like this. This gives you a very perfect detector performance, right? So you can design the threshold much more efficiently such that your probability of false alarm is very low, and at the same time you can give a very high value of PD. Okay, So, and the way to characterize even this ROC is using the area under the curve of this ROC function or ROC plot, right? So what we can do is, as you saw, this is good, right? This is a good ROC curve, whereas this is a very poor ROC curve. And the metric that is used is the area under the curve in this ROC curve. So if we take integral of this particular portion from let's say 0 to 1, so the PFA could be 1 and this is 0. So what is the area here? So this is known as AUC criteria or area under the ROC curve criterion, right? So if the area of the ROC under the ROC curve is higher for a certain detector, of course that is a better detector compared to where you had the lower value of area under the curve, area under the ROC curve. Yeah, so yeah, this is till this much I wanted to cover today. So this is about event detection and how to develop a formal framework of doing event detection. Once you start working with sensors, we collect the data. We have to just, instead of using a randomly chosen threshold, this is trying to give you a more educated guess to design the value of threshold. Okay, so that's mathematical nitty-gritty details. Please try to take one more look at it, and I'll also share you some materials that you can refer, right, for the Nyman-Pearson part and the receiver operating characteristics part. Right, for the beginning, you don't have to refer to any particular material per se for knowing about the different kinds of sensors. You can just browse different online available materials or materials from similar courses, right, which are taken in different universities. So that will be sufficient. Okay, and I'll share some more materials for this part only. And later in the next class, we are going to do work more on the quantization, ADC, and so on. Right? We mentioned about the discretization in sampling, how the amplitude could be discretized. So those kind of things we will discuss.